Hello everybody. Today we are going to be going over circles and their properties in terms of geometry and including with interior and exterior angles. So here we have a circle with a radius of 6. A radius is essentially a line extending out from the center of the circle that is equidistant to the edge of the circle. So a radius, let's say here, that red and blue are equal, and so is this. So are those two lines. So this radius can give us a few things. For example, let's reference some formulas here. The circumference, which is essentially the length around the circle, is equal to 2 pi times the radius. The area of a circle is going to equal pi r squared. And the diameter is going to equal 2 times the radius. So let's find these things. So 2 pi times 6. So in this case, the circumference of this is 12 pi units. This case, pi times 6 squared. 6 squared is 36, and 36 times pi is 36 pi. So that's how many, we might as well specify units squared. The diameter is d equals 2r, so 2 times 6 is 12 units. So that's how you find all of the like area, circumference, diameter, and things like that. Now let's get on to arcs in a circle and angles specifically. So let's say that we have a line extending from the center here. Say this is let's call this the center. And we have another line here. And then we have one last line right here. So let's call this 195 degrees. Now, let's call this 60 degrees. In this case, what I reference by the black is that this entire thing is 195 degrees. So, we got to find this. Let's actually give these names A, B, C, D. So we got to find this arc AB. AB is less than 180 degrees because 180 degrees is a straight line, but a full circle is 360 degrees. So if we have our 195 and we subtract that from 360, we should get this arc AB. Essentially, it has a central angle that it casts out onto the circle. Think about like the moon in real life casting shadows. So when we subtract these two, we are going to get 165 degrees. So that means let's label this 165. And now we could try to find arc ADC. Or in this case, arc AC, because it is less than 180 degrees. So let's say that we have the whole arc being 195, and we have this little portion here being 60. So 195 minus 60, which equals 135. So that means that this portion here is 135. So essentially, we can assume that since this is the center, let's call this the center, if and only if the center is that, then it's going to cast out a shadow of 165 degrees, known as an arc. So in this case, this is the purple arc. This is the blue arc. And this is the black arc. So that's how you find the arc lengths of central or arc measures of central angles when it comes to that thing. A central angle is just an angle that is created by two radii in the center of the circle. Now, let's go over some other properties of circles. So, we have arc length. Essentially, our arc length, here I'll update the graphic. Okay, now let's say that we have a line here. Let's say we want to find the arc length of this major arc. So the major arc is going to be the one that's over 180 degrees. So let's highlight that. Let's use purple. So this is going to be the major arc. I'll draw it a little more accurately. There we go. So that's going to be the major arc. Let's say that this arc right here is about, I would say, 130 degrees. We have to try to find that purple arc, and let's find the arc length too. So let's have let's have it that the angles in a circle are equal to 360 degrees. So if this is 130, and then we have the rest of it is 360 minus 130, which is equal to 230 degrees. Now, we have this formula. S is equal to radius times angle in radians. So if we convert 230 degrees into radians, all we have to do is multiply it by pi over 180. And if you want to do the opposite of this and turn radians into degrees, you multiply by 180 over pi to cancel out the pi's. So let's cancel out our zeros. And we have no factors really, so this is just 23 over 18 pi is going to be that section of this. So if S equals r theta, theta is just some angle, that means that our arc length here is going to be S. Well, let's actually assign a radius here. Let's give a radius of 6. Or, well, actually, here's a better number. Let's go 9. So if 9 is our radius here, what is our arc length? Well, this means that this one is also 9. So S is equal to, the radius is 9, times 23 pi over 18. Now let's make some adjustments. This turns into 1 and this turns into 2 with cross cancellation. So now it is just 23 halves pi. So that is the arc length of this major arc. Now, if you want to look at the minor arc, well, we can just take the circumference of the circle, which is 2 pi r, so 2 pi times 9, which is equal to 18 pi. And we can say that this 23 halves pi plus x is going to equal this 18 pi. So let's actually convert this 18 right here into 36 halves, just to make it easier to subtract. So x is going to equal 13 halves pi. So this means that this arc length here, I'll highlight it in blue, this arc length here is 13 halves pi. And this arc length is 23 halves pi. And together they add up to the circumference, which is 36 pi, or sorry, it is 18 pi, sorry. So that's how you find arc lengths when given the radius. Now, if you're given the circumference, you can either set up a proportion or solve for the radius. Let's view some angle theorems specifically for this one. So let me erase all of this. All right. So going to create some lines here. Now, let's say that we have some lines that are intersecting outside of this circle. Let's say that we have this red angle. This red angle, let's say it's about, probably good to make it 46 degrees. Now, let's say that we have this angle right here, and this arc here, essentially, it's going to be a central angle. So, theoretically, in the center of the circle, there's a casted shadow on that arc. It's just you can't see it because it's not directly in the center. So, you can't really see it. But if it's ever asked you to find an arc length like that, it means it from the center of the angle. And it's not equal to the thing that casts it out. So this means that this little arc length here, I'll highlight in, I guess, blue. This arc length in blue is not equal to 46 degrees because this arc length is actually based on a central angle. And this little point right here, this is an exterior point. This is an exterior point. So it's only in the center if it casts that shadow. But let's say that this is, I don't know, let's say 65 degrees. Actually, we'll use a different number. Probably, let's go 66. We'll use 68. So, if that is 68 degrees and that is 46 degrees, let's say we call this arc K. So that arc K right there is going to have a special relationship to those two angles. So we're going to have it that our K minus our 68 times 1/2 is going to equal 46 degrees. So we can tell that the purple angle and the blue angle, the blue minus the purple, is going to equal the 46, well, times 2. So if we multiply by 2 on both sides, we get K minus 68 is equal to 92. Now all we got to do is add back 68, and then we get 160 degrees as our K. So that's how you find it when you have one exterior point or an exterior angle and also an arc. Either that sometimes the smaller part of the circle or that is created on the edge of the circle, which in this case is the blue region. But the formula is reversible, of course. So let's move on. Let's say that we have all right, very interesting. So let's say we have some chords. What chords are essentially just lines that have some intersections with the circle, or that have only intersections with the circle. It doesn't have to pass through the center like radii do. So they're not equal to radii. So not all chords are equal. And now, it is good to mention that radii are chords, but chords are not always radii. So let's take these chords, for example. They don't even have to intersect in the center, but let's say that one of these, let's call this is a red region, and let's call this a blue region. Let me rewrite that. So, that red region, let's call it 75 degrees. Well, actually, we're going to call this one, I probably should use the same color. Let's call this one 75 degrees. And let's call this one 33. Oops, wrong color again. 33 degrees. Okay, let's try to find this angle. Let's call it alpha. So we're going to use a theorem that essentially states that we have half of the sum of these two arcs is going to equal that alpha. And in this case, half of 33 plus 75, well, 33 plus 75 is just 108 over 2 is going to equal alpha. So alpha is going to equal, in this case, let me actually draw that better. Give me a second. Alpha is going to equal, well, 108 divided by 2 is 54. So that's going to equal 54 degrees, and so is this. Which means that this angle, I'll highlight it in green, is equal to, well, 180 minus 54, which is 126. In this case, obviously not drawn to scale. So that's how you take intersecting chords and their arcs and set up a relationship between them. Now, let's tackle something else here. So let's say we have something like this. Let's say that this angle is 88 degrees. And let's say there is an intersection of this here on the edge of the circle. Let's find this red region here. So the way to do that is actually very, very simple. All we have to do is take 2 times our interior angle, which is 88, and that's it. So 176 degrees is going to equal that red region. Now, obviously, if we had our arc already and we wanted to try to find that interior angle, we're going to have to multiply by 1/2 and then get 88. So that's a very simple formula there. All right. Next, we're going to use some tangent line theorems. The tangent line only touches the circle once. So let's set it up. Let's say we have a secant line. It touches the circle twice, essentially. And then let's say we have a point of tangency, I would say about right here. Okay, so let's say we have an exterior point. We have some exterior length measure. So this is 9. Like from here to here, this little portion is 9. And let's say this is 15. Let's find this thing. Let's call this length U. So this length, so essentially the thing is that with this, our 15 squared, so our tangent line length squared is going to equal our little portion times the bigger portion. Well, what I mean by the bigger portion, I mean the whole thing. So it's not 9 times u, it's 9 times 9 plus u, because u could be anything. So we need to make 9 plus u. So let's distribute. Well, first of all, let's simplify. 225 is equal to 9 times 9 is 81 plus 9u. So now we can just subtract 81 on both sides. We're going to have 9u equals 144. 44. And then we can just divide by 9 on both sides. And then we know that u equals, u equals 16. So that's our answer there. So this u portion here is 16, which means that this entire thing is 9 plus 16, which in this case is 25. So that's how you use tangent lines and secant lines to solve for lengths. Let's go over one more concept. So we're going to be inscribing shapes here. So when we inscribe shapes, essentially what we're doing is we're putting a shape inside of another shape, and it carries special properties. So let's create some endpoints here, and let's try to make a quadrilateral inside of this particular circle. So let's draw the lines. It doesn't necessarily have to be a square or rectangle. This one isn't. There we go. So we have a quadrilateral here, and let's use some variables here. Let's say that this side here is 2x plus 18. And let's say this side here is 25x. Obviously not drawn to scale. Let's find x. Find x and the angle measures. Let's call 2x plus 18 alpha, and then let's call 25x beta. So let's say that we essentially have this theorem where the opposite sides of a quadrilateral that is inscribed inside of that circle are supplementary. Supplementary means add to 180. So 2x plus 18 plus 25x is going to equal 180. Now, we just combine like terms. It's going to equal 180. So let's subtract 18. 27x is going to equal 162. And now we know that it divides nicely into 6. Now, let's find alpha. So alpha is going to equal, well, we said that alpha was 2x plus 18, and 2 times 6 is 12. 12 plus 18 is 30, meaning that if they're supplementary, that means we don't need to plug in 6 to 25x. We just already know that beta equals 150, because 150 plus 30 is equal to 180, because they're supplementary. So those are some theorems, some very common theorems that relate to circles and things inside of them as well, including some properties with shapes and arcs, and how to find arc length and arc measures. So I hope you liked the video, and I do appreciate everyone who watches the videos, and I'll be obviously posting more videos relating to Algebra 1, geometry, or any other subject in the near future. So hope everyone has a good day, and goodbye.